Hi guys, Miss Barber here. This lesson is titled Combinations. We begin with a discovery assignment. Consider the following groupings of the letters A, B, C, and D taken 3 at a time. The first column starts with ABC, and the 5 rows that follow is every possible permutation of ABC. For example, it follows with ACB, BAC, BCA, CAB, and CBA. The next column takes ABD and follows it with 5 rows of every possible permutation of ABD. Likewise, for the third row, the 3 letters selected are A, C, and D, and the 5 rows that follow give the remaining 5 permutations of the letters A, C, D. And finally, the fourth column takes the 3 letters B, C, D, and in the 5 rows that follow provides the remaining 5 permutations of the letters B, C, and D. Part A. How many permutations are there? We've got 4 columns by 6 rows, or you could individually count each of the permutations. Regardless of the way you choose to do it, you get 24. Now, the next question is how many groupings are there if the order of the selections don't matter? If we look at the first column where it's ABC and all entries below that is a different permutation of those 3 letters, then actually it's just ABC. The second column is ABD and all the permutations of ABD. So if the order doesn't matter, then we can represent ABD with 1 ticket that has ABD. Similarly, for the third column, where we have ACD and all permutations of the letters ACD, if all we want is a grouping, then we can represent everything in that column with ACD, and likewise for the fourth column, we can represent all 6 of those if only thing we're concerned with the grouping as BCD. So let's go back. How many groupings are there if the order of the selections do not matter? And we see that there is only 4. Definition. A combination is an ordered arrangement of items such that all selections come from a single group of items. No item is selected more than once. This is also often called no repetition. And the order of arrangements do not matter. We have a formula for that. Combinations of n things taken r at a time can be written as C subscript n comma r is equal to n factorial divided by the quantity n minus r factorial times r factorial. Example, 2 representatives from the 500 Emerald Eagles are to be chosen to speak to the university president. And how many ways can this be done? Notice that we are working with a combination, as all selections come from a single group. They're all Emerald Eagles. No item is to be selected more than once. We can't have the one person be 2 representatives. And finally, the order of arrangements do not matter. As long as we get 2 representatives, we're good. So we'll use the formula C sub n comma r is equal to n factorial divided by the quantity n minus r factorial times r factorial. Let's figure out the parts. The number of items selected is 2. We've got 2 representatives. The number of items in the group is 500. Now write that formula again, but this time putting in 500 for the n and 2 for the r. C subscript 500 comma 2 is equal to 500 factorial divided by the quantity 500 minus 2, that would be 498 factorial times 2 factorial. You can and should use your calculator to compute combinations. On the TI-84, press 500 for 500. The keystrokes to get to the combination tool, select Math. Scroll right to PROB, suggests probability. Scroll down to small n, big C, small r. Looks like combination. Press enter. And then in the blinking space, put in 2. Your screen should have 500 C2. Now press enter. The result is 124,750. Example. Suppose a 5-card poker hand is dealt to you. And how many different ways can this be done? This is a combination, as all selections come from a single group of items. Here the single group is a deck of cards. No item is selected more than once. It's a 5-card hand. And finally, the order of arrangements do not matter. Thus, we'll use the combination formula. C sub n comma r is equal to n factorial divided by the quantity n minus r factorial times r factorial. Let's determine n and r. First, we'll begin with the number of items selected. It's a 5-card hand. Now, the number of items in the group. It's a standard 52-card deck. Let's rewrite that combinations formula, putting in 52 for the n and 5 for the r. The formula becomes C subscript 52 comma 5 is equal to 52 factorial divided by the quantity 52 minus 5 factorial times 5 factorial. The count here is 2,598,960. Example. Determine if combinations or permutations should be used to answer each of the following questions, and then compute the counts. Some may use both or neither. Part A. In how many ways can a person, vice chairperson, a secretary, and a treasurer be chosen from a group of 15 people if one person cannot hold more than one position? Because order matters, that is, there are specific positions, this is a permutation. There are 15 in the group and we choose 4, so that's 15 permute 4. Use your calculator to compute. 32,760. Part B. In how many ways can a subcommittee of 4 people be chosen from a group of 15? Sounds similar to Part A, however, we just need any 4 people. In this case, that's a combination because the order or the arrangement doesn't matter. So this would be 15 choose 4. Use your calculator to compute, and you find out there's 1,365 different ways in which a subcommittee of 4 can be selected. Part C. In how many ways can 2 kids' names be picked out of a group of 4 kids to determine who gets the last 2 identical pieces of pie? Notice, last 2 identical pieces of pie, so the order or arrangement doesn't matter. This is a combination as well. There's 4 kids, only 2 gets it. This is a combination, 4 choose 2. You can use your calculator to compute. The number is 6. Part D. There are 7 red tickets and 4 yellow tickets in a box. In how many ways can 5 red and 2 yellow tickets be drawn from that box? We begin this as a counting principle problem, as you're doing 2 events. One is to select red tickets, the other is yellow tickets. However, this is also a combination, as you want any 5 of the 7 red tickets, so that would be 7 choose 5, and you want any 2 of the 4 yellow tickets, so that would be 4 choose 2. Use your calculator to compute. 7 choose 5, that's 21. Use your calculator to compute. 4 choose 2, that's 6. The product of 21 and 6 is 126. Part E. In how many ways can a 5-question assessment be written if the first 3 questions have 4 possible answer choices and the last 2 have 2 possible answer choices? This is a counting principle problem. We've got 5 test questions. The first one has 4 possible answer choices, as well as the second and the third. The last 2 have 2 possible answer choices each. The product gives us the total possible set of answers you can have, and that's 256. Example, answer each of the questions. Part A. A political party has 6 persons from which to choose a presidential and vice presidential candidate. How many different tickets are available to the voters? Let's observe that president and vice president are distinct positions. The order or arrangement here matters, so we're looking at a permutation. We've got 6 candidates, want 2. That would be 6 permute 2. Use your calculator to compute. 30. Part B. An access code consists of 2 digits selected from the 6 digits 3, 4, 5, 6, 7, and 8. Digits may be repeated. How many distinct access codes are possible? This is a counting principle problem. We've got 2 digits. We've got 6 choices for the first digit, and because we can repeat digits, we also have 6 digits to choose for the second, the product of which is 36. Part C. You have 6 quarters in your pocket and need 2 to pay for a soda. How many choices do you have when deciding which 2 quarters to use? The order doesn't matter, so this is a combination problem. That is, you'll have 6 choose 2, and that computes to 15. Let's make some observations. 1. Each of the previous selects 2 items from a group of 6. 2. 2 of the previous do not allow repeats or repetitions. Combinations, permutations do not allow repetition. And 3, each of the 3 have different counts. Example, from a standard 52 card deck, how many 5 card hands will have 2 clubs and 3 hearts? We begin this count with the counting principle. We've got 2 different types of cards. We need some clubs and hearts. Now we're going to use combinations to determine how many different ways we can get 2 clubs. There are 13 clubs in a standard 52 card deck, and we need any 2. Order doesn't matter. So that'll be 13 choose 2. And we'll multiply that to we need 3 of 13 hearts. So that'll be 13 choose 3. Now use your calculator to compute the combinations. 13 choose 2, that's 78. 13 choose 3, that's 286. The product of 78 and 286 is 22,308. Example: a catering service offers 8 appetizers, 10 main courses, and 7 desserts. A banquet committee is to select 3 appetizers, 4 main courses, and 2 desserts. How many ways can this be done? We'll begin by using the counting principle, knowing that we've got 3 dishes to pick. We need an appetizer, we need a main course, and of course we got to have dessert. Now we're going to use the method of combinations. There are 8 appetizers and we need to select any 3. The order in which we choose them don't matter, so that'll be 8, choose 3. For the main courses, we've got 10 to choose from and we've got to pick 4. That would be 10, choose 4. And finally for the desserts, they have 7, we need 2, so it'll be 7, choose 2. Now, use your calculator to get the counts for each of these combinations. 8, choose 3 is 56. 10, choose 4 is 210. 7, choose 2 is 21. Multiply 56 and 210 and 21. The product is 246,960. Example: there are 8 standard classifications of blood type. An examination for prospective laboratory technicians consists of having each candidate determine the type for 5 blood samples. How many different examinations can be given if, Part A, all of the test samples provided for the candidate are of a different type? That means no repetition, and the order in which they're identified is very important. They're different blood types, so this is a permutation. 8 blood types, you pick 5. That'll be 8 permute 5. Use your calculator to compute. 6,720. Part B. 2 or more of the test samples can have the same blood type. 2 or more can be the same means repetition is okay. Thus, we'll use the counting principle. 5 vials of blood. You've got 8 choices for the first. Repetition is okay, so you have 8 choices for the second. As for the third, fourth, and fifth, this is 8 to the 5th, or 32,768 different possible examinations.